Swayam Prabha. Digital India. Educated India.
Okay, so we're back to business. We are continuing with this. Today we will be talking quite a bit about, mainly about the supported oxides, the role of additives, coverage, support effect, getting into complementary operando and in situ studies to understand what is happening. You see that usually Raman and infrared are highly complementary, and I will be playing with these two techniques. And so one of the stories I want to start with is catalysts where you have not one supported oxide, but two supported oxides, two transition elements like vanadium and molybdenum oxides. So typically, mixed molybdenum vanadium oxides are used for many hydrocarbon oxidation reactions to oxygenates or to make also like olefins. So I'm looking at it in this case for propane ODH, oxidative dehydrogenation, which goes to propylene. And so we are dealing with samples, like you can get references like vanadium oxide on alumina, molybdenum oxide on alumina, and the two of them on alumina. So basically, I mean, rather than weight %, we are talking about atoms per square nanometer, because you know that about 8 makes a monolayer. So basically you see 3 and 3 makes 6 below monolayer, 5 and 5 makes 10 above monolayer. So you will know if they are dealing with dispersed oxides or there is no space for all of them to be dispersed, and then they will have to somehow aggregate or interact. So scenario will typically be if you have a low coverage and you have dispersed vanadium and dispersed molybdenum, they may stay around. How much they like each other is part of the question, whether they stay separate or they will connect with each other. This is also part of the reason of what is happening and how this is affecting the performance. So you increase the coverage, they will be more polymerized than isolated, and of course above the dispersion limit you will get vanadium pentoxide crystallites or molybdenum trioxide crystallites, or maybe mixed oxide phases. So when you look at the catalyst before and after reaction, that's very hot here. Can we get colder air conditioning? Yeah, it's very hot. So basically, the fresh catalyst will look like this. And here you have a Raman bands at different values, around 1,000 and around 900 plus, which basically is the oxo group of vanadium oxygen, the vanadyl, isolated vanadium oxide species, or MO, isolated molybdenum oxide species. So you can see the two of them are there. Here, this is molybdenum and vanadium, 5 moly vanadia. So it's like 2.5 moly, 2.5 vanadia to make this 5. Down here, you only have moly. So you get the band at about 900. Now, you also see other bands, which are present here. And when you are looking at the used catalyst, what you see is that new bands grow stronger. Like for instance, this one at 230 and 750 that were already present here. So there are some changes on this material. And the way the catalyst behaves depends on the total loading, also on whether you have only molybdenum, only vanadium, or molybdenum and vanadium. So some of the drawings are not appearing, which is a little bit misleading, but basically what is happening is molybdenum alumina low coverage, you basically have dispersed molybdenum. And this catalyst is working in a discrete manner. At given temperature, you get some conversions, but you have to heat a lot to get the propane conversion. Now, when you are dealing with the vanadium catalyst on alumina, with a VO bond characteristic at 1030, the system is more active. And when you are using this molybdenum vanadium catalyst, basically you get the very similar performance. when we make the operando study of this catalyst during reaction, what is happening is interesting. This is a catalyst that we are running as we increase the temperature. So basically at 200 degrees there is no reaction. And then as you increase the temperature, 320, 340, the catalyst is working. You are getting some CO, CO2, and propylene, which is your idea. Now what happens is that you have this mixed oxide phase between molybdenum and vanadium. As you increase temperature, they break. They spread, and in the end you have like dispersed vanadium and dispersed molybdenum. So the structure that you are getting, this mixed oxide, breaks during reaction. And if you remember, the performance of molybdenum vanadium and only vanadium was very similar. So it means that the presence of molybdenum was not relevant. If you look at here, this molybvanadium or vanadium, both of them have the same performance. And basically what it's telling us is like, dispersed molybdenum is not very active. If I have a surface where we have a few dispersed molybdenum and a few dispersed vanadium, basically each of them is running on its own. And the total contribution of molybdenum is very low. Actually, at 200 plus, molybdenum affords a conversion near zero. So basically at this temperature, vanadium is giving a conversion and molybdenum is given a negligible conversion. So basically you see no difference. So yes, the fresh catalyst has like a mixed phase, but the first thing that happens to this mixed phase is that it breaks, it spreads, and it gets two individual. And one of them at this temperature is basically non-active, and the other one is active. So basically the coexistence of molybdenum along with vanadium at very low coverage is kind of irrelevant. It's not doing anything, which is basically what we see here. Because this mixed phase basically disappears. It breaks into dispersed moly, which is hardly active, and dispersed vanadium, which is working at these temperatures. So basically this is the scenario, this mixed phase where basically is vanadium that has been distorted by some moly that gets into the lattice, but that one breaks, and when you are at working conditions, basically you get the dispersed phases. Now here we are looking also at catalysts with increasing loadings, like this is very low loading, and basically it breaks and spreads. And as you increase the coverage, you will see that sometimes there are Raman bands associated with mixed phases on these two elements on the surface. And that was associated, I'm sorry, there is a missing slide here. Okay, basically this system where you have the mixed phase, and that the mixed phase remains after the reaction, the conversion was a bit better and the selectivity was much better. So there should have been a slide showing that, I mean, the key message, and then I will, because there was no slide, I will draw it. You have moly and vanadium on alumina catalyst. At low coverage, basically this one will remain dispersed, this one will remain dispersed, and at 300 plus, this one is doing some activity, this one is doing very little activity, so the presence of this one at low coverage is irrelevant because they are spread and basically this one is hardly active. But at higher coverage, you have more and more, all of them. And then in the end, they will connect and there will be an interaction between these two oxides and then you get a mixed phase. And in this case, the system has a similar performance than the only vanadium, but the selectivity was better. And actually, in that case, you do have Raman bands of this mixed phase between molybdenum and vanadium that remain stable in the system. There is one scenario when you are using additives and promoters that you will see. There are some additives that don't like to interact with each other. Like for instance, vanadium and molybdenum, they are acidic. So acidic and acidic, they don't really attract each other that much. However, if you put something which is like more acidic and something that is more basic, then they will like each other. So you will see like there are different kind of additives that you can call maybe like interacting ones or non-interacting ones. So an interacting and non-interacting, this is not official, this is just an internal message. For instance, interacting is if you are adding vanadium. Okay, basically let's say like that. This is like low and high coverage. If they are interacting elements like for instance vanadium or molybdenum and sodium, like we saw on the earlier days, they immediately form some kind of alkali vanadates or alkali molybdates. So they do form compounds. So they like each other even at very low loading. Remember, like we were saying, like you put a ppm of sodium, and the vanadium, the molybdenum, is affected by this ppm of sodium. So basically they are interacting. Of course, at high coverage, when you are above the monolayer, they will also interact, but above monolayer they have to interact because there is no space for them, so they have to mix. Those that you consider like non-interacting can be, for instance, molybdenum and vanadium. At low coverage, if there is space for both of them, they will be sitting nearby, they will not really interact, and each one will be doing its job. So somehow it's like they don't interact between each other. So this is like non-interacting. So at low coverage, they don't interact. At high coverage, above the monolayer, in the end, they will make something because there is not a space for all of them together. So in such a case, they will interact. So somehow, whether I define those additives like or two components like interacting, non-interacting, is because the way they interact with each other at low coverage, when there is a space for both of them. If they don't really have an affinity, they will sit here and you will sit there because there is plenty of space. But if there is an affinity, even if when there is plenty of space, they will be nearby. So this is a reason. And that is important because when we are talking about systems in general, you are talking about supported oxides, and you have a coverage, can be the coverage of a single element of the total coverage of several elements. And you will have one or no more additives, and this additive can have like high affinity or low affinity for each other. And then you will see that depending on the support and depending on the coverage, you will see like no interaction or you will see interactions. And those things basically affect the performance. So one case of mixed oxides that in principle do not appear to have interaction is vanadium and antimony. These are two elements which are used, for instance, in catalysis for amoxidation of propane to acrylonitrile. Amoxidation is a reaction where you make this acrylonitrile, which was a work made by Olga. And basically, this paper is interesting because that was the first paper using the word operando. So this is a very old story, but fortunately it's true. I was not wrong, and the story from here remains valid, which is also important. What happens with propane? Propane, you may have two kinds of reactions. You can be converting propane to propylene. This is oxidative dehydrogenation, where basically you feed oxygen and propane in air, but the reactive one is oxygen and propane, so that you get propylene and water. Well, you also get a little bit of carbon monoxide or carbon dioxide, but the target product, the one you want to get, is propylene. If you run amoxidation, that's another reaction where you make a nitrile. In such a case, you are feeding oxygen, but you are also feeding ammonia. And then the propane will go into a nitrile, which is acrylonitrile. So here you have the nitrile group at the end of the hydrocarbon. And of course, water is produced, and some other products get like CO2 to make them out. Even propylene is also observed in this reaction. So not all the propane goes to acrylonitrile, but you may get a little bit of propylene. This catalyst is an industrial catalyst, which is basically bulk vanadium antimonate. And because it is a bulk vanadium antimonate, when you want to get into the understanding of what is the relationship between the catalyst structure and the catalyst performance, you may be losing part of the information if something is happening at the surface, like what if we have some dispersed antimony, or if we have some dispersed vanadium. Could we have like this kind of dispersed phases at the surface of the vanadium antimonate? Remember iron molybdate? In the end, the surface was covered by a monolayer of molybdenum at the surface of this iron molybdate. Now here, do we have those things? Well, literature didn't know because they were typically working with bulk oxides. So our approach was not only to make operando study, but also we were considering that if we use the bulk system for the operando study, we may come into the paradigm of planet Earth. There is no life on Earth. So we wanted to go into smaller particles to be able to see what happens in the surface without a very, very intense overwhelming signal from the bulk. How we do that? Similar to the nanoseria particles of the other day. We put a very small amount of this vanadium and antimony on a support. A very small amount means around one monolayer, maybe 2 monolayers, maybe 3 monolayers, maybe below monolayer, and make some kind of aggregate. Well, it turns out that vanadium and antimony, they are mainly like non-interacting, which means that a low coverage below monolayer, they basically stay one next to the other, and antimony is hardly reactive. So the performance of a low-loading vanadium antimony, well, you have, for instance, 1/3 of a monolayer of vanadium, 1/3 of a monolayer of antimony, that makes 2/3. It's below monolayer. So they stay dispersed. And the performance is almost the same with or without antimony, because basically the one doing some reaction is vanadium, and at this low loading, basically, without antimony, you will get propylene, but you will not get acrylonitrile, which is associated with this vanadium antimonate phase. If you have a monolayer or more than a monolayer, so you can put like half a monolayer of vanadium, half a monolayer of antimony, that would be the minimum, then you do get the vanadium antimonate, and then you do have propane oxidation. If you put 2, 3, 4 monolayers, again, you will get the propane oxidation. Of course, the more monolayers you have, the larger the vanadium antimonate crystals are. And we wanted to have the minimum expression of a vanadium antimonate crystals. So we tried several series, and the story I'm going to tell you is about 1 monolayer. So it was half of a vanadium, half of antimony. That was the minimum amount to create a vanadium antimonate. So in the possible scenarios with 1 monolayer, maybe everything will be like a vanadium antimonate, or maybe they remain like half antimony, half vanadium, or maybe they segregate like a crystalline vanadium or crystalline antimony. That is very unlikely, because even if they are not interacting, if there is a mixed phase, that mixed phase will form. So the chances of getting vanadium antimonate was very high. So we make the catalyst, and the interesting thing is that when you make the catalyst, at the beginning, after calcination, even when we were just at 1 monolayer, basically we didn't see a mixed phase. We only saw the Raman bands of dispersed vanadium, vanadyl group here, and the VOV here. But there is no signal of antimony. Antimony has bands like you see over there in this low frequency region, but there was no evidence of antimony whatsoever. Well, okay. But then we decided to start running the reaction. And the interesting thing is that when you start running propane and oxidation, and you start to flow propane, oxygen, and ammonia, what you see is that the Raman spectrum of the supported vanadium oxide starts to look different. That's difficult to tell what it is. But if you look at the evolution, basically what you see is that something is happening to the vanadium. And that something in the end is actually the formation of these 2 bands very nearby, which are bands characteristic of vanadium antimonate. So the interesting thing is like this dispersed vanadium and that dispersed antimony, even if you make calcination at 1 monolayer, they just, okay, hi, hello, but they don't really interact. They only say hello because they are very polite elements, that's it. But then when you are doing catalysis, something is happening, and somehow they blend, they combine into something. And then you start to get the vanadium antimonate. So the reaction is actually the driving force to make the mixed phase. And many times in catalysis, even when you get to 2 elements, the more extensive formation of a mixed phase only happens during a dynamic state, during reaction, which makes sense, because when you are heating, but nothing special happens to the catalyst except that it gets hotter and hotter. But during reaction, it's not only that you increase temperature, bonds are continuously being formed and broken. And then the chances that they bind like this or eventually they bind like that is higher. And actually this is what is happening. And then you see the buildup of something which is no longer dispersed vanadium or dispersed antimony, but the vanadium antimonate phase, which structure you see here, it has a rutile structure. And as you increase temperature, this new phase is increasingly apparent and evident. So here you get a pretty nice Raman bands of vanadium antimonate. The nice thing is that this spectrum is already 480, and when you have a clear formation of the vanadium antimonate, you get a pretty nice yield to acrylonitrile, 29.2% yield to acrylonitrile, 30% basically. Now the question is, okay, we get vanadium antimonate and we get propane oxidation. We also get a little bit of acetonitrile, propylene, whatever, but the most important product is acrylonitrile. Now the question is it a good catalyst or is it a bad catalyst? good and bad, is something relative. So is good compared to what? I say, well, obviously, compared to the industrial vanadium antimonide catalyst. So if you go to the patent of the original vanadium antimonide catalyst, a patent, pure vanadium antimonide with any promoter, any additive or anything, but just the basic vanadium antimonide, those patents are reporting 30% yield to vanadium antimonide. Now here, this catalyst is affording 30% vanadium antimonide. So, well, that's nice. It is performing like the patents of the basic vanadium antimonide catalyst, but there is one very important difference. Those patents are using 100% vanadium antimonide, and here we have one monolayer, like 90+% of the sample is alumina, inexpensive, economic, and only a little bit is vanadium antimonide, but that little bit is all you need, because in the case of the bulk vanadium antimonide, most of it is inside. The molecules, they don't know if inside this particle you have more vanadium antimonide or you have cookies. They don't know, they only interact with the surface. Now, in this case, what we have is nanoparticles of vanadium antimonide with very highly exposed surface. And the performance is the same. So that was a good point, because then we can say, okay, it is working. Now, the next question is, what can we tell about this reaction? So the first thing that we could see about this reaction is that this antimony oxide that was dispersed, that it was not apparent, during reaction it becomes apparent like segregated Sb2O4 and also like vanadium antimonide. So somehow the antimony, a little bit was like segregated Sb2O4 crystalline, and a little bit was vanadium antimonide. So everything rearranges. But the most important thing is that you get the mixed phase. Now, after reaction, we decide to reoxidize. What happens with reoxidize? We don't break the vanadium antimonide. The vanadium antimonide remains, which is the top spectrum. So here you reoxidize, and the vanadium antimonide is there. Interestingly, the Raman bands of the segregated vanadium Sb2O4 are no longer present, and you get a stronger band of dispersed vanadium. So somehow, like vanadium and antimony mix into the vanadium antimonide, and during reaction you get this vanadium antimonide with a little bit of segregated antimony. You reoxidize, the segregated antimony disappears, and a little bit of vanadium appears. So somehow there appears to be like a dynamic state, like vanadium antimonide is kind of, depending on whether you are doing amoxidation or reoxidizing, like maybe vanadium goes in and antimony goes out, and if you reoxidize, antimony goes in and vanadium goes out. It's kind of like vanadium antimonide appears to have a role not only for the reaction but also for the exchange or interaction between these two species. If you reoxidize, obviously you are dealing with oxidative conditions. If you're running propane amoxidation, okay, you are also doing an oxidation, but you also have ammonia, and the conditions are not that oxidative, they are slightly more reductive. So somehow it's more like a slightly more reductive and a slightly more oxidative conditions. And that is affecting this equilibrium of the fellows outside of the vanadium antimonide lattice. And the key message also about the particle size is that when you are dealing with a large or a nanoparticle, when you are dealing with a large particle, you cannot see the bulk compared to, you cannot see the surface compared to the bulk. When you go nano, you have a lot more surface compared to bulk, and you can see more things, and we do see like dispersed vanadium. People couldn't see dispersed vanadium in the bulk vanadium antimonide. And probably the dispersed vanadium has a role on this reaction. And people couldn't see like segregated antimony, they only saw vanadium antimonide. And probably the segregated antimony also has a role. At least we see an interplay that is not only vanadium antimonide, but dispersed vanadium appears and disappears, segregated antimony appears and disappears. Of course, making a nano per se is difficult. That's why we use a support to stabilize the nano, so that they don't sinter and they don't fly away, and you can run the reaction. Okay, so what we observe is that we only get propane oxidation when the vanadium antimonide phase forms. Now, the question that remains here is vanadium antimonide the active phase, or is vanadium antimonide like a necessary partner, and maybe the dispersed vanadium or the dispersed antimony are doing the job, or it is all of them, or two of them? That we cannot tell yet. We see that you get the vanadium antimonide and something happens. And basically, from structural point of view, this is what we see. That the first catalyst had like dispersed vanadium, some dispersed antimony which is amorphous and has no Raman signal, but during reaction, part of this antimony, along with part of this vanadium, makes the vanadium antimonate. And another part goes into Sb2O4. A group in Madrid made a very interesting microscopy study about vanadium antimonates. And what they did is to look at the structure. This is a rutile material, and the composition of vanadium antimonate has vanadium 4+, vanadium 3+, antimony 5+ cations. So this is what you have inside that lattice. And they were looking at changing the partial pressure of oxygen with a transmission microscopy and observe the crystalline phases. And what they were observing is that there was an increasing number of vacancies in the system when you were decreasing the partial pressure of oxygen. And when you did that, what was happening is that antimony atoms were getting out of the lattice. It's a very dynamic system, and just by removing oxygen, which is kind of a, I shouldn't say reducing, but not oxidizing anymore. So it's like a moderate reducing conditions, because you make vacuum and you minimize the partial pressure for oxygen, that really tends to reduce. And then all of a sudden, the system responds by losing antimony on the side. So basically the vanadium antimony ratio, which is typically 1:1 in this system, and VSB04, as you decrease the partial pressure of oxygen, what happens is that you get an increasing excess of vanadium. That means that antimony is getting out of the lattice. And they observed those changes were very reversible. And that was telling you, okay, this system is extremely dynamic. Even if you not only do reduction, you don't even use hydrogen, but if you just reduce the partial pressure of oxygen, there is a structural change in this system. And actually, there was a group doing calculations about the mobility of antimony cations in this lattice, and it has a very low activation barrier for the mobility of the antimony cations, which means that these cations very easily go in and out of the lattice. And that means that if conditions are slightly more oxidizing or slightly more reducing, it will have an effect that you experimentally see even with the microscope. And that is consistent with the fact that during propane oxidation, because of the ammonia, there will be some tendency for a little bit more of reduction, and then you see antimony coming out. And then when you reoxidize, antimony goes back in. Somehow, you are getting a response on the other side because some dispersed vanadium appears on the system. And that is something which is relevant because also when you do reaction, that we also see similar changes in a reversible manner. Mainly, you have the fresh catalyst with dispersed vanadium and dispersed antimony. During reaction, you create this vanadium antimonate with segregated antimony phase. When we were reoxidizing, basically the dispersed antimony disappeared, which was SbOx amorphous phase, and you restore like dispersed vanadium, and the vanadium antimonate essentially is there. If we were looking at different stoichiometries of vanadium antimony. In some catalysts, we have even higher amount of antimony, and in this case, it was interesting because you go from Sb2O4 to Sb2O3. So basically, what happens is that in the end, the amount of segregated antimony decreased, either from Sb2O4 to Sb2O3 or to an amorphous one. This one is apparent in Raman, this one is not apparent in Raman, and you have different bands. So basically, what happens is you create the phase. If you reoxidize, you lose the dispersed antimony. And if you go back to reaction, you restore the dispersed antimony, and activity data you see is the same yield to the acrylonitrile, propylene, CO2, and acetonitrile. So it's completely reversible changes again and again and again. So something is happening that continuously is moving these ions in and out of the lattice. And like I say, if you use a higher amount of antimony, the segregated antimony phase, instead of disappearing, goes into Sb2O3, which is this one. And if you are 1:1, it goes from Sb2O4 to no band. Of course, with a large excess of antimony, you see Sb2O3, and then when you see Sb2O4, it is stronger, but always is the same thing. So you get a segregated antimony that decreases and goes to another phase, or basically disappears. But there is always a change between the antimony, the vanadium antimonate, and the segregated vanadium. And that is also very important because the Raman bands that we see is vanadium during reoxidation, and a Raman band at about 1060, and a Raman band at about 660 during reaction. 1060 and 660, I've been telling you many things during the last week, but you have to remember these frequencies for one reason. hydrocarbons connecting to supported vanadium have Raman bands at about 1060. So you have a vanadium on a support, and then you get vanadium alkoxides. You have vibrations at about 1060 and 660 wave numbers. And we are observing something here. So the question is, maybe because we see this vanadium alkoxide, that the dispersed vanadium is doing something, activating the propane, and then the propane goes into the vanadium antimonide to the reaction, probably. But the question is, where do you make acrylonitrile? Where does ammonia goes? Does also ammonia goes to the vanadium? Does ammonia goes to the antimonide? Does ammonia go to the segregated antimony? So what is the process in this reaction? What we know is that when you're running reaction, the dispersed vanadium are less apparent and they go into alkoxides. This one doesn't change and you get more segregated antimony. And if you reoxidize, the presence of this decreases and the other one increase. So the point is, where is propane actually activated, here or there? And where do we activate ammonia? So to get an additional insight, we do computational chemistry. This is Professor Monica Calatayud from Paris. And she was helping us to get the psychology, the rationale behind what is happening on the catalyst, somehow like the reasons, the rationale, the affinities, and what is changing. Now, by using computational chemistry, you can calculate the affinities, but also the repulsion. So you can find whether there is an affinity or there is some repulsion. The same way that happens with people may also happen with people. By the way, this photo was taken in the metro in New Delhi. And for some reason, we were taking a seats for old people or mentally challenged, I don't know, whatever. So we were there. So she was doing the calculations for us about the affinity of the different sites at the surface of the vanadium antimonide with propane and with ammonia to see how the reaction is happening. So what she was calculating, we sent a postdoc to her group to make these studies. And basically what we were making is, okay, there is vanadium site in gray, there's antimony side in yellow, the red one is oxygen, and this is the hydrocarbon. So molecules which are present in the reaction, at least that we know, is propane, because we are feeding propane, so propane is one of the reactants, ammonia is the other reactant, and then we calculate those things. So how does propane like to bind to this vanadium side? Okay, absorption energy is like 2.9, okay, it's not particularly exciting. It's quite happy absorbing with this configuration here. I'm particularly happy there. The absorption energy there is like minus 30. Okay, so that's kilojoules per mole. That's a good value. So this is between these three, and this side with this configuration is the most likely absorption of propane on this side. Okay. Antimony? Propane doesn't really like antimony because the absorption energies here is very little stabilization. It only decreases by 5.6, and in this case, it doesn't like it because even the energy increases, and if you increase the energy, this is not a favorable process. So if propane is going to absorb somewhere, it will be essentially at the vanadium sites, which makes sense because usually vanadium is a catalyst used for hydrocarbon oxidation, so it would make sense that propane will be activated to propylene on the lattice vanadium sites of the vanadium antimonide. Okay. We also see that another reaction product is propylene. So we also calculated where does propylene like to absorb. And in this case, what we find is that propylene is very happy to absorb basically on vanadium side and also on antimony side, and pretty much with the same energy, stability, absorption energy, like 19 and 19 negative kilojoule per mole. So while propane only likes to bind to the vanadium sides, propylene likes to bind to the vanadium and to the antimony side. Okay, and the absorption energies were like 30 for the propane and like 20 for the propylene on both sides. So during reaction, let's assume that you get the propane molecule, it goes and it absorbs on the antimony side. Absorption energy of propane on antimony side is very little, it doesn't really like it. And if it were activated here and propylene well formed, when the molecule absorbed there like propane, is not very happy. But when it goes into propylene, the absorption energy is much higher. It's like 20 against 5, which means that once that you get propylene in that site, so strongly bound, propane is not able to kick it out because the absorption energy is higher. So that means that if the reaction were happening there, you already go from propane to propylene, and that's the end of the reaction. So you immediately block the site. Okay, so let's think what happens if propane goes to the vanadium side. Propane absorbs in the vanadium side with an energy of 30. Okay, and then propane is converted to propylene, and propylene absorbs there with an energy of 20, which is okay, because when a fresh propane molecule comes in, it has a strong absorption energy, so we'll easily kick out the propylene from there, and then you are restoring the active site. Fine, perfect, so the vanadium antimonate is working and we are converting propane to propylene, which is part of the reaction, but we are not making propylene. We are looking for acrylonitrile. And then we have to see what happens with ammonia, and where does ammonia bind? We agree that propane can easily go to propylene on vanadium antimonate, yes. But now where does ammonia absorb? When you're doing an oxidation of propylene, ammonia absorbs also on the vanadium side. This is the side it likes the more. But if propane absorbs with an energy of 30, and propylene is absorbed with energy of 20, that can easily be replaced. But then you flow ammonia, and ammonia goes there with an energy of 60. What does it mean? Much stronger. So who is going to kick it out? Exactly. And who can push ammonia away? With an energy of 30 against 60? No. Ammonia will sit there and nobody will go there, because propane absorbs stronger than propylene, but it is 30, it's half the energy of the absorption of ammonia. So ammonia says, I come here and I stay here, and that's the end of the movie. So on pure vanadium antimonate, you cannot run propane oxidation, because in the end, as soon as you have ammonia, you are killing the only possible site. Now, is there any way around it? How can we get the reaction running? Sorry. Yeah, but you cannot make ammonia less strong. I mean, ammonia has a nature that absorbs with the energy of 60 on the vanadium side. It doesn't matter, because even if you reduce the concentration of ammonia, it will sit there. So you have to think that there may be something else. Is there any other active site where the molecules like to absorb? Did propylene like any other site? Like, for instance, the antimony site? Because vanadium doesn't care about antimony site. But propylene can go to the propylene site. So let us forget for a moment that we are doing propane oxidation. Imagine we are doing propylene oxidation. If we do propylene oxidation, then that's convenient, because ammonia binds here on the vanadium side, and then on the neighbor side, you get propylene. So you forget about propane. If you are only feeding propylene and ammonia, okay, ammonia here, propylene there, hello, hello, nice meeting you, shall we go for a coffee? And in the end, they marry, because they are nearby, and there is a chance for them that they will react, and something happens. And acrylonitrile prefers to bind at the vanadium site, which is where ammonia was. So this is something that would make sense. Question?
So we'd like to answer, there is a question from online participant.
Okay.
So they would like to know that how the energy is calculated.
Well, we were using density functional theory. Basically, to do that, you have to describe the lattice of the vanadium antimonate, which is a rutile structure, like the one I'm drawing. This is just the surface of the rutile lattice structure. It's a periodic model, so you make a cell unit and you repeat ad infinitum. So you can calculate what happens at the surface of this material when you're absorbing molecules, like propane, propylene, oxygen, ammonia, and that's made by computational chemistry, density functional theory calculations. And then you can observe how strong different molecules are absorbing on different sites. And now, the point is, when you are getting ammonia and propylene nearby, they can easily react, and the preferred site of absorption of the acrylonitrile is on the vanadium sites where ammonia was sitting. So somehow that is nice, because the absorption energy of acrylonitrile there is 30. So when you get fresh ammonia with an energy of 60, it will push the acrylonitrile away, and then you're restoring the active site. And the antimony is again available to continue the reaction. So according to these calculations, propylene oxidation may occur on the vanadium antimonate. That's very nice, but we are feeding propane, we are not feeding propylene. So how can we go around that? Because we are not really feeding propylene, or are we? When you go back to the propane oxidation data, operando, you see the formation of vanadium antimonate. And you see that the vanadyl bond transforms when you are running reoxidation, you go to reaction to a band at 660 and a band at 1060 and a band at 660. If you remember the other day with methanol chemisorption, 660 and 660 are the alkoxide bonds. So that's the formation of propane bonded to the dispersed vanadium. A vanadium oxygen carbon bond vibration, it will be the same for a methoxy than for a propoxy molecule. So basically, vanadium antimonate may not activate propane because ammonia will prevent that site to activate propane, but dispersed vanadia is nearby. And dispersed vanadia we see on the operando Raman studies that is actually activating propane because you are getting the vanadium alkoxide formation. So actually, here you see the 1060 and 660 that you see from vanadium alkoxide is also typical for propane alkoxide. So 1060, 660, 1060, and 660. So basically, again here you see the vanadium alkoxide there and there. And actually, this is what appears to be happening. Without the dispersed vanadia, this reaction could not occur. You need the dispersed vanadium, and the dispersed vanadium is actually the one which is converting the propane to the propylene. And that is the propylene, the one who goes to the vanadium antimonate where ammonia is also binding. And then you get the acrylonitrile. Yes?
So what about the absorption energy of ammonia and the dispersed vanadium?
It is much lower than that one of vanadium, of propane.
But the both are the vanadium. I mean, the dispersed
Yeah, exactly. Both of them are vanadium, but this is vanadium dispersed on alumina, and the other one is lattice vanadium in vanadium antimonate. So the environment is totally different because this is vanadium oxygen aluminum, the bridging oxygens around it, and the other one is vanadium oxygen antimony because it's vanadium within the antimonate lattice, and the other one is vanadium on alumina. So the nature of the vanadium is very different. In one case, and actually experimentally, you see the formation of the alkoxides, and in the other side, basically you see how this propylene is the one reacting. So you are combining the operando studies with the results that you are obtaining catalytically and with the computational calculations. And then all together are telling you a story that you couldn't tell if you didn't make operando studies, and also if you didn't use nanoscale particles, because without nanoscale particles, you will not be able to see the dispersed vanadia or dispersed antimony phases. And then you can see all the interplay. And then the segregated antimony appears to be more on a, not a catalytic cycle, but a structural cycle facilitating that the vanadium antimonate is under more oxidative or reducing conditions. So this is adding like some structural flexibility of the system during the reaction. So that is interesting because the oxidation capacity of the vanadium antimonate is very high actually, and if you make a methanol TPSR of the supported of the vanadium antimonate or supported on alumina, here you can see two kinds of products from the methanol TPSR. When you make a TPSR, acidic sites will convert this methanol into dimethyl ether, and of course you have several catalysts, and alumina support is very acidic, you get a lot of dimethyl ether. Antimony is also giving dimethyl ether, and different catalysts are giving you very few dimethyl ether. Actually, the catalyst that we are using, the good one, which has this monolayer of vanadium antimony and alumina, has practically no acidity. It's covering the alumina support, so the alumina acidity is basically cancelled because it's covered by a monolayer. But when you look at the redox, that's very interesting because basically the supported vanadia has a redox activity. It produces formaldehyde at 197, which is, if you make TPSR, is quite a good value. And the other phases are more or less okay, but the interesting thing is that this catalyst with the monolayers of vanadium antimony is producing formaldehyde at 150, which is among the lowest temperatures that we have seen and Israel has seen when you are making TPSR. So it's a very good efficient oxidation catalyst, very active even at very low temperatures. So the vanadium antimony has very special properties, but it gets blocked because of ammonia. The real catalyst has defects or has promoters that induce the creation of defects at the surface of these sites. And so we also decided to calculate what happens if there were defects. And defects means like eventually there is an antimony, there's a vacancy. And we know there are vacancies because during the reaction, antimony goes in and out of the structure. And there was already a calculation by a group in Argentina demonstrating that the migration of antimony ions in and out of the vanadium antimony is very easy. There's very low activation energy barrier. The microscopy people show that indeed this happens very easily. And then we want to say, okay, what happens if there is a defect, like vacancy of antimony, on the absorption of the different molecules? And then we were looking at the absorption of different reactants, like with ethane and ethylene, propane, propylene, and ammonia. So we were looking, because we were using the system for ethane and propane and oxidation. In all the cases, the absorption energy is more favorable, it's a more negative value, means there is a higher stabilization. So the molecules are much more happy binding to a defective structure than to a perfect structure. And basically, this is something that we already know, that the catalysts are like the people and that defects make them interesting. So also for the molecules, this defect makes them interesting. And we know that the vanadium antimonate spontaneously generates defects because antimony goes out during the reaction. And industrial catalysts, actually, titanium doping, aluminum doping by Brasdil, which is from British Petroleum, which are the industrial catalysts used for this, they were using titanium and aluminum actually to promote the presence of these defects, which basically resulting in this weak Raman band at about 800 palas because of these defects. We were doing something similar, adding niobium, it was the same effect again. So the presence of defects is indeed further increasing the performance of this catalyst for propane and oxidation. So, well, that was part of the story. Now, another kind of reactions that you can also make is the production not of acrylonitrile from a C3 molecule that you go from propane to acrylonitrile, but another important reaction is the conversion of ethane to acetonitrile. In this case, you go from 2 carbons to 2 carbons with the nitrogen, CCN, and then you get the nitrile group here. For this reaction, vanadium antimonate is okay, but there are mixed oxides that are very efficient for this reaction. And so we have a catalyst prepared where we are dispersing nickel and niobium oxides. So basically, you are dealing with these niobium oxides where you are dispersing nickel oxides, and the synthesis is by mixing 2 powders, and the nickel powder and the niobium oxide powder. And you mix the 2 powders and then you get the nanoparticles dispersed on the surface of this material. And the interesting thing of this system is that after calcination, you will get different phases. Of course, if you are dealing with pure nickel, basically you get the Raman bands of pure nickel or the diffraction pattern of pure nickel. If you have pure niobia, you will get the Raman bands of pure niobia or the diffraction pattern of pure niobia. And when you have a mixture between 0 to 100% nickel niobium on nickel oxide or niobium oxide, what you start to observe is another Raman band that corresponds to the mixed nickel niobium phase. So depending on the loading, you can have dispersion, only a bulk nickel, bulk niobia, or a mixed nickel niobia. And the idea is to understand which one is the active phase that is doing that. In the case of X-ray diffraction, basically what you see is a worsening of the diffraction pattern of nickel, but you cannot clearly get much about the development of niobium. So that niobium phase that we are getting here must be quite amorphous because it doesn't show you in the X-ray, and actually the X-ray becomes like very broad, very noisy. So this is telling you most of the sample is not pure crystalline, it's like some kind of ill-defined phases. The way these catalysts behave depending on the nickel niobium loading is presented here, and at very low loadings, of niobium, where you only have nickel on a little bit of niobium, the system is basically converting ethane into ethylene quite efficiently, and also to acetonitrile. So like somehow the loading is defining like two regions. One region that is very interesting, where you have the mixed nickel niobium phase that Raman was telling you, and that mixed phase is actually very good to make ethylene, which is up there. Sorry. And for acetonitrile, you have basically a small loading, like 10% loading of niobium and nickel is when you get a maximum in the production of acetonitrile. So somehow we have two maximas. Depending on the loading, the catalyst can be very good to make acetonitrile, or can be very good to make ethylene. And it depends on the relative loading. So we wanted to understand what was the active phase making nickel niobate, because in this catalyst that was very good to make acetonitrile, you don't see nickel niobate. You only see nickel and a little bit of segregated niobium. So we decided to make a operando Raman study of this system. First of all, what happens with the stability? Because when you prepare the catalyst, you have the nickel and the niobium. And if you remember, 10% niobium in nickel basically shows only the Raman band of nickel, and you hardly see any niobium in the system. And actually, you don't see even nickel niobate, even if you hit the sample up to 500 degrees centigrade, or you reoxidize after that. So somehow the nickel and the niobium do not interact when you are heating in air. But this is just a TPO in situ Raman. Now, you only see the nickel. What happens to niobium? Well, you don't see. But if you run the ethane ammoxidation reaction, we were doing it in this temperature interval. And during ammoxidation, things are different. You do get the nickel, of course, but you start to see the development of additional Raman bands during reaction that you didn't observe here, not even at 500 plus. So there is something happening already at 300-400 degrees, which is that during reaction, these two oxides are no longer sitting nearby, but because of the oxidation reaction, bonds are being formed and broken, and eventually they start to mix. And even when you don't get any mixed oxide, even after several hours at 550, during reaction in few minutes, you get at significantly lower temperature these new Raman bands that correspond to the nickel niobate phases. So you are developing this mixed phase, and you're not only developing the mixed phase, but at the same time you start to see the conversion of ethane to ethylene and also to acetonitrile. So again, the solid state reaction in the material is triggered by catalysis itself, and very often the active phase is not formed when you do the synthesis of the catalyst, when you do the calcination or any treatment of the catalyst, but during the reaction itself. And the reaction itself shapes the catalyst according actually to its conditions. So very often the real actual catalyst is formed during the reaction. You've seen it for ethane ammoxidation, you have seen it for propane ammoxidation, you have seen it for methanol oxidation. So many times this is what is happening on these materials. Well, this is like additional data, but I've been too slow, and this is just going around the same story. I don't want to. Even if you go and make with a high resolution transmission electron microscopy, you can make electron diffraction in small areas. And by electron diffraction, you can determine what crystalline phase you have. And then you can also observe that depending on the catalyst composition, like 10% niobium or 80% niobium, when you look at the mixed nickel niobium phase, the atomic composition is very different. You get a niobium rich or a niobium pure mixed phase. And actually, you can see the Raman bands are different from the nickel rich or the niobium rich nickel niobate. So Raman bands can also be associated in combination with the microscopy to which kind of niobium rich or nickel rich phase you are getting on the system. But that is already something formed. And we have been seeing how a catalyst is born, how a catalyst phase develops, and then the other thing that you can see is how a catalyst dies. That this was a work of the thesis of Martinez Huerta, and Ana Iglesias was helping us with the synchrotron studies. This is a system, vanadium oxide on Syria, in which what you are observing is that the catalyst deactivates. And by looking at the deactivation of the catalyst, you can get an insight on the structure-activity relationships of the catalyst. So basically, you can see things from the life of a catalyst, from the birth of the catalyst, but also from the death of a catalyst. In this case, it is a catalyst that, as a fresh one, is a nice active catalyst, but during reaction, it dies, it deactivates. And this is a catalyst which is basically vanadium oxide dispersed on ceria. And the vanadium oxide dispersed on ceria can be easily characterized because the vanadium oxobond is at about 1030, which is this band here. So here you have a family of catalysts from naked ceria all the way up to 5 weight % vanadium oxide on ceria. You get a very strong Raman band of the ceria support, which is over here. But as typically happens with many oxides in Raman, they have a strong band, but doesn't really prevent you to observe what is happening on the supported oxides. Most of the important bands of the supported oxides are here, and these can be seen. Basically, what you see is that as you increase vanadium coverage, you get a stronger Raman band of the vanadyl group, 1030. And as you increase the coverage, you also see another band growing at about 950, which corresponds to the polymeric VOV bonds. So you are having more and more vanadium, at the beginning isolated, later on polymerized, and at the end, with the 5 weight %, you start to see like new bands, like this one here, which is already corresponding to crystalline vanadium pentoxide, but nanoparticles. Most of it will be dispersed vanadium. When you are looking at the supported vanadium, and you see a Raman band at about 1030, okay, this is the vanadyl mode, and this is dispersed vanadium. When you start to see vanadium crystals, very suddenly you see like a sharp band at about 990. This corresponds to crystalline V2O5. Now, even when this band is stronger than this one, the Raman section of the crystallites is very high. It was calculated to be like 20 times higher. So even when you get this signal, the reality corresponds to something 20 times smaller, which tells you that the Raman is extremely sensitive even to nanocrystallites. And also, when you see that this band is stronger than that one, that doesn't mean that you have many more crystals than dispersed, because this is apparently bigger. The intensity of the Raman cross section of crystallites is about 20 times stronger than the intensity of dispersed vanadium. So even if you see these sharp bands, like we observe here, like there is a little sharp band already, like 990, like this little bump here, or that one at there, that means that you are just getting the minimum expression of the vanadium pentoxide crystallite. Raman is reporting that nicely. X-ray will not be able to report it because it's below 3 nanometer, but it is very sensitive. So basically this is slightly above the monolayer, and 90% will be dispersed vanadium and a little bit crystalline vanadium. What happens with this catalyst when you use it in reaction? Well, we use it for ethane oxidative dehydrogenation, ethane to ethylene. After the reaction, this catalyst is deactivated, and the Raman bands for pure ceria, well, doesn't change. But for the vanadium oxide on ceria, basically you hardly see any dispersed vanadium, and you see new Raman bands over here and over there. These new Raman bands correspond to cerium vanadate. So in this case, the catalyst is deactivated because the vanadium has reacted with the support, making cerium vanadate. And in the end, this is like when you have a vanadium, titanium, and you make rutile. The surface vanadium disappears. You are losing active phases. You are going into some phase that is no longer active. And then you know that this is what is killing the catalyst. So this is a very interesting system if you want to make an operando study to see how the catalyst deactivates. And when you do the operando study on the deactivation of this catalyst, you get very complex things because it was not as linear as expected, because the idea is I lose surface vanadium, I get cerium vanadate, and the catalyst dies. And we were expecting to see simultaneously the loss of dispersed vanadium and the deactivation of the catalyst. However, the situation was a little bit more complex, and the story that at the end we can tell out of that is because we are making an operando study, and we are simultaneously looking at what happens to the structure and to the activity. Because if you make reaction in situ, you are assuming a deactivation associated to the formation of cerium vanadate, and you miss a very interesting detail, which is the following. If you look at this conversion temperature plot, this is from the operando reactor, and these are the spectra in the operando reactor. Now the nice thing is that 450 to 500 C, the conversion of ethane is increasing according to the Arrhenius plot, which basically is telling you that the nature of the active site is not changing. Okay, above 500 degrees C, there is a strong deactivation of the catalyst. So I got it, cerium vanadate. Okay, and then if you keep on heating, of course activity will increase, but it will be lower than it should have been. So the catalyst is deactivated. And they say, okay, let's try to regenerate the catalyst. How do you typically, try to reoxidize, see what happens. You reoxidize, but the catalyst is still down there. You cannot regenerate. So whatever is happening is irreversibly deactivating the catalyst. And we know what happens, cerium vanadate. Now the surprise was that, okay, the catalyst dies above 500 degrees C, like 520, 530, 540, 550. So cerium vanadate will be forming above 500. However, operando spectra show that already at 460, 490, you already have cerium vanadate. And then we have a problem because the catalyst was okay, dispersed vanadium was doing the work, and why do we get the deactivation, I mean the solid state reaction before we see the deactivation? Yeah, the phase that you have now is the phase I had when I saw this data. No, it doesn't make sense. How do I explain that? Then you also go not only into the quantity, but also into the quality of the spectra. If you see above 500 degrees C, the Raman spectra of cerium vanadate, they would look a lot better, sharper, better defined, stronger. Signal to noise ratio is much lower. So like this cerium vanadate is much better defined above 500 degrees centigrade. So somehow this is telling us, okay, there is something else. Dispersed vanadium is not incipient cerium vanadate is not really killing the catalyst, but the well-developed cerium vanadate is killing the catalyst. Would that make sense? How would I explain that? And then you start thinking, okay, we have dispersed vanadium, incipient cerium vanadate and dispersed vanadium, no dispersed vanadium and cerium vanadate. So something is happening here, and whatever is happening here is not really affecting the reaction, because this shaded region is that shaded region where conversion increases with temperature, according to Arrhenius plot. Whatever is happening is not affecting the nature of the catalyst. So if we make a cartoon, basically what you obtain is like, there is something here interesting, because you can make a Arrhenius plot, and here you have the fresh catalyst before the solid state reaction. You can see that the apparent activation energy doesn't change, but the interesting thing is that as soon as you are doing this reaction, over here you have dispersed vanadium, over here you have dispersed vanadium and incipient cerium vanadate, and over here you essentially have only incipient cerium vanadate, and everything falls in the same line. So wherever it is not really affecting the catalyst. Then when you get the deactivation, all the Arrhenius plot data are down here. And the interesting thing is that after the solid state deactivation, the activation energy, which is the slope of this line, is essentially the same. So basically you are dealing with the same apparent activation energy. So before and after the activation, Arrhenius is telling you, look, the nature of the active site appears to be the same, which is telling me, okay, the active site, whatever it is something that exists on the supported vanadium on ceria and on the cerium vanadate, because the nature of the active site is not changing. The only thing that really changes upon the activation is the pre-exponential factor. You can see it's the same slope, but it's smaller. So the nature of the active site is not changing, but you have a lower number of people doing the job. So we have like two clues out of the Arrhenius plot. Nature of the site is not changing, but the number is decreasing. And then there is something that you have on supported vanadium on ceria and on cerium vanadate, which is a common functionality that would account for the job. And the only common functionality that you can think of is the bridging oxygen between vanadium and cerium, because you have bridging oxygens between vanadium and cerium on the supported catalyst, vanadium, oxygen, cerium, and in the cerium vanadate, vanadium, oxygen, cerium, and in the incipient cerium vanadate, where you have vanadium, oxygen, cerium. Now, the point is that during the incipient deactivation of the catalyst, the number of these bridging oxygens which remains exposed to the molecules doesn't change significantly. It means like a very incipient formation of cerium vanadate will result in the same number of exposed bridging oxygens here and here, and that has no effect on the activity. And if you hit more and you get a much better defined cerium vanadate phase, then you get a better defined phase, but then the fraction that is exposed is lower because you get a better three-dimensional development. That would make sense, except because we have a small problem. Cerium vanadate is vanadium 5 plus, okay, but cerium 3 plus. And dispersed vanadium ceria is vanadium 5 plus, but cerium 4 plus. So the bridging oxygen is actually not equivalent because in both cases vanadium is 5 plus, but at the other side you have cerium 3 plus. Cannot be the same size. But everything is telling you that supported vanadium and incipient cerium vanadate, they are very much alike. And then we say, okay, fine. Out of desperation, say, well, maybe the interface is reduced. Why not? It's a crazy idea, perhaps, but we have to double check. Because if the interface between vanadium and ceria were reduced, then this bridging oxygen will be totally equivalent in both cases, vanadium oxygen cerium 3 and vanadium oxygen cerium 3. How can we verify that indeed vanadium ceria and the incipient cerium vanadate are very much alike? How can we be sure that the vanadium is 5 plus always? And how can we be sure that the cerium at the interface with vanadium is 3 plus? Well, Raman cannot tell you all these things, but the synchrotron technique can help you, directly or indirectly. These are the synchrotron measurements of vanadium oxide on ceria. And here you have the catalyst in air at 300, at reaction at 300, in air at 800, and the reference bulk cerium vanadate. The first thing that you see is that the first shell of vanadium on ceria looks very much like the first shell of cerium vanadate. So the environment of vanadium already on ceria, even if you don't see cerium vanadate, looks very much the same. So this is telling you, okay, structurally, they already look very much alike. Vanadium is 5 plus. Vanadium doesn't reduce because even at 800 degrees C, the synchrotron is telling you that this is vanadium 5. No matter what you do, it doesn't reduce. That is also very significant because usually supported vanadium has a little bit of vanadium 4 plus because of the conditions, because of some polymeric vanadium may have a little bit of 4 plus, but no here. Everything is 5 plus, absolutely, which is very special. It's telling you, wow, that means a very strong interaction with ceria. And what can we tell about ceria? Well, we try synchrotron, but because ceria particles are larger, you get a huge signal from the bulk, and you cannot tell what happens at the surface of ceria. Like there is no life on Earth. It's too big to be able to detect something at the surface. But EPR, electron paramagnetic resonance, you could see very weak signals associated with cerium 3 plus. So the EPR was telling you, you do have a little bit of cerium 3. It doesn't tell you where, but you do. And it also tells you like the more vanadium we have, the more cerium 3 we have. And where is this cerium 3? Well, this is true that it increases quite in parallel with vanadium loading, but that doesn't mean that it is next to it. What we did is oxygen pulses. If you make oxygen pulses in the EPR experiment, you could see how this oxygen was titrating the cerium 3 defects, which was telling you, okay, these cerium 3 defects are at the surface. Okay, if it is at the surface, maybe close to the vanadium at the surface. Okay, but we couldn't tell. So there was a moment that there was a lot of evidence is telling us that interface is reduced. But the best we could do is to make a drawing like this, so the ceria is this yellow thing, and then we make a black carpet, and vanadium is in the black carpet. This is like a reduced ceria. But then we need, again, computational chemistry, density functional theory. This is a system that we were not used to it, or my colleague Monica in Paris, but there was a group in Berlin, Joachim Sauer, and he's a major expert on ceria. He has made all kinds of calculations for ceria. He has actually calculated cerium vanadate. So he had all the ingredients, And he has been working with vanadium on other supports. So I went to Berlin, said, look, Joachim, we have all this data strongly suggesting us that the interface between vanadium and cerium is reduced. But we don't get the direct evidence of that. Can you calculate what happens when we disperse vanadium on ceria? And what will happen, what will be the structure of these cerium atoms at the interface if they reduce? And he said yes. And a couple of years later, they came out with this paper where basically what they were observing that indeed the cerium atoms at the interface between vanadium and ceria are reduced. So the light blue is cerium 4+, the dark blue or black is reduced cerium. And where is the reduced ceria? Right at the interface between vanadium and cerium. So that is ideal because basically this is what we were indirectly observing, even when we didn't have a direct evidence for that. And we were also telling Joachim, look, if we try to reduce vanadium, it's impossible. Even at 800 degrees with the strongly reducing conditions, vanadium is 5+. And he calculated the reduction of vanadium, and basically what happens is that if you try to reduce vanadium to vanadium 4, the energy of the system increases by 1.5 electron volt. That means impossible in the computational chemistry calculations, which is exactly what we were observing, that this is not happening. And therefore, as we were assuming, indeed, the interface is reduced and the redox cycle will be occurring between the vanadium and the ceria atoms. So we have this cartoon, and Joachim made something much more professional, showing that. So that is ideal. So the cartoon is in 2000, this is 2009, but in the end, everything is consistent. That is very nice. But then we can say, okay, I want to see the ceria. I want to see. If I don't see it, if I don't touch it, I don't have a strong evidence because computational chemistry is perfect, it's ideal, but is just modeling with very high chances to be consistent, to explain everything, but you really want to get the direct experimental evidence. So again, what we did is supported nanoscale particles support, stabilizing and support. So we made nanoceria on top of silica. Then when you have nanoceria, the surface to volume ratio is very high, and if something happens at the surface of ceria, you can see that. And then the group of Jimirm in Taiwan prepared this nanoscale ceria at the surface of silica, and then we could impregnate vanadium, so that the vanadium will be at the surface of ceria, and then Ana Iglesias with the synchrotron would measure what was happening with the vanadium and with the cerium edge. And this is what we observe at the synchrotron with the cerium, which is basically that for the catalyst during reaction, there is a reduction of cerium. If you reoxidize, you flow in oxygen 800 degrees C. Basically, the catalyst is reoxidized and the cerium is reoxidized to cerium 4+. And if you go back to the reaction, it's completely reversible. You see black and green. It goes back to a reduced phase. We were working on this catalyst, which was 3 weight % ceria on silica, and on top of which we were adding 1, 2, 3 weight % of vanadium, so that you have very nice coverage of the ceria nanoparticles with vanadium. And the nice thing is that when you integrate the amount of reduced and oxidized ceria, what you observe is that during oxidative dehydrogenation reaction, ceria is completely reduced. For 1 weight % on this 3% ceria, 2% on the 3% ceria, and 3% on the 3% ceria. But the nice thing is that when you reoxidize the catalyst, if you have a little bit of vanadium, my friend, a fraction of the ceria is not reoxidized. What fraction of the ceria? Well, it must be the ceria interacting with vanadium. That gets like cerium 3+. And even if you are oxidizing at 800 degrees, say, no, I like it like that. I stay like 3+ at the interface with vanadium. You have more amount of vanadium on this system, and what happens is that the fraction of ceria that remains reduced is higher because you are increasing the coverage. So basically this is telling you like you have a higher coverage of vanadium with ceria, and that certainly indeed at the interface this cerium is reduced. And you put a little bit more and we were close to the monolayer, so the trend was kind of leveling off. Again, you see the same thing. So that was a direct evidence that indeed the interaction between the vanadium and the ceria is resulting in the stabilization of this cerium 3+ at the interface. The one on the right is cerium vanadate, which is cerium 3+, no matter what you do, even if you want to reoxidize crazily, the structure is cerium 3+. So everything's 3+, no matter what you do. But indeed, this was demonstrating how the interface is reduced. And that is very nice, because we couldn't have made all this way if we have not made an operando study where we see that we lose vanadium, we develop cerium vanadate, and nothing happens. That the activation happens later when there's a more extensive formation of cerium vanadate. That's the reason why going from reaction in situ to operando makes a difference, because you can connect events at the given moment, what structure and what activity you have. And then you go into this adventure, and then you can tell this story. But there is even more. Okay, this is just the same explanation. About the formation of cerium vanadate. Because if you hit the catalyst, it will ultimately make cerium vanadate. 2 weight % vanadium oxide on ceria. You increase the temperature, and just by heating in air, the surface vanadium will disappear. And basically, as the surface vanadium disappears, it starts to disappear, you start to see the cerium vanadate. And when you're running out of surface vanadium, everything is cerium vanadate. And the remaining of ceria remains like bulk ceria. Why did we make that? Well, again, this catalyst is running on a redox cycle. So you want to know the boundary conditions, which is what happens if you heat in hydrogen and what happens if you heat in oxygen. So this is the in situ TPO Raman that you want to compare with the in situ TPR Raman. Okay, this is the development of the cerium vanadate. And you start to get the formation of cerium vanadate, perhaps, if you are generous, at 600, but very clearly at 625. Now, this is a redox cycle, like I say. So the catalyst is being continuously reduced and reoxidized. So boundary conditions is total oxidation, total hydrogenation. So let us look at these two extreme scenarios. And also, we were already expecting that the formation of cerium vanadate will be facilitated in hydrogen. Why? If you look at this table, why would you expect that heating in hydrogen will facilitate the formation of cerium vanadate? Exactly, because the cerium vanadate is more reduced. So ultimately, this is a stable structure, and in oxidizing conditions, the system ends up reducing. But if the system is more reduced and you do it in hydrogen, things will happen before. And does it happen before? Yes, it does. Here you have a blow up of this region when you make a TPR Raman, and basically you get the surface vanadium, how it decreases, and how you start to get the formation of, this may appear something that it's clearly on the way to the cerium vanadate, and at 450 it is clearly cerium vanadate. Now, this is about 200 degrees before. That's dramatic. You are forming the cerium vanadate 200 degrees before because you are in hydrogen, you are in a reducing environment. Now, during a redox cycle, are you oxidizing the catalyst? Not exactly. You are reoxidizing the catalyst. During a redox cycle, are you reducing the catalyst? Well, to some extent, the catalyst is being continuously reduce and reoxidize, reduce and reoxidize. So, are you here during the redox cycle? Not exactly. Are you there during a redox cycle? Not exactly. And are you somewhere in between these two? Yes. And this is actually what is happening. This catalyst is making the cerium vanadate at about 600. In hydrogen, about 400. During reaction, it deactivates at 500. You are somewhere in between. So the catalyst is reduced and reoxidized, and when the catalyst is reduced, chances are that it goes into the cerium vanadate. And that is an irreversible change. And because it's a redox cycle and bonds are being formed and broken, once that you start something, it's difficult to stop. And then that accounts for the fact that during the oxidative dehydrogenation of ethane, the catalyst forms cerium vanadate. But there is even another story which is very interesting. You remember vanadium titanium, you remember the TPR, you remember the hydrogen consumption. So hydrogen consumption is because vanadium was being reduced from vanadium 5 to vanadium 3. Supported vanadium on almost any oxide reduces, and always the TPR profile is the reduction of vanadium, correct? Yes. So when you look at the TPR of the vanadium oxide on ceria, the first thing we thought was, okay, this hydrogen consumption during the TPR of vanadium Syria is obviously the reduction of vanadium. And that's what I told to my student, and she was happy, and I was happy. But then, when we start to make all the studies, we realized that vanadium never reduces on Syria. So when you are making a TPR and you see this reduction of hydrogen about 400 plus, which is very similar to reduction temperature of vanadium, titania, alumina, ceria, zirconia, okay, so it's the same. I said, no, vanadium doesn't reduce. So what are we measuring with this reduction peak here? The reduction of something, because we are consuming hydrogen, the reduction of Syria. We are measuring the reduction of Syria. So we are revisiting the typical TPR profiles of supported vanadium, which is always the reduction of vanadium on all the supports except Syria. In the case of Syria, when you get this peak, no, this is not the reduction of vanadium, this is the reduction of Syria. And not only the reduction of Syria, it's the reduction of Syria when it is being converted into cerium vanadate. And actually, 2% vanadium oxide on Syria has a reduction peak with a maximum at 475. Temperature program reduction in situ Raman shows 400, 450, a clear evolution of this dispersed vanadium into the cerium vanadate. 450, so it's something over here. It's basically confirming that this hydrogen TPR profile of the supported vanadium is not the reduction of vanadium, but the reduction of the Syria support, which was also a very interesting revisiting of this tendency. Yes, okay, there's a question. Stay tuned.
So during the reaction, cerium is getting reduced to cerium 4 plus to cerium 3 plus.
Yeah, it's been reduced to cerium 3 plus, yeah.
So in the TPR, we understood that there is a hydrogen environment, so it is getting reduced. In the TPR, we understood that it was a hydrogen environment, so it has been reduced. Cerium 4 plus to 3 plus.
Yeah.
In case of during the reaction, what was the driving force that cerium 4 plus to cerium 3 plus?
The driving force, it is a redox cycle. So the vanadium Syria is oxidizing ethane to ethylene and water. So in the end, when you are making a reaction, you got ethane. So you have CH3, CH3. Here you have the vanadium Syria catalyst. And after this reaction, what you get is CH2, CH2, and water. So this water has two hydrogens, which is one from here, and an oxygen coming from here. So when you make ethylene, this catalyst is being reduced by ethane. You make ethylene and water. And then the catalyst, by giving out this oxygen, is being reduced. And then you are also feeding oxygen. So this oxygen goes into the lattice to restore this vacancy that you have created. That's a redox cycle. The catalyst is being reduced by hydrocarbon, and then you are continuously regenerating by the gas phase molecular oxygen. So this is the driving force reducing, and that is triggering the conversion into the cerium vanadate. And now, yes, we have coffee, and stay tuned, we're back in 15 minutes.